Hello again. This is Math 2232, coming to you from the College of DuPage. The title of this lecture is Integration Using Tables and Computer Algebra Systems. As always, please be attentive while watching this video. In this video, we describe how to use tables and computer algebra systems to integrate functions that have elementary antiderivatives. Now, in other lectures, we're explaining that all functions don't have elementary antiderivatives, but that is why you end up resorting to using tables and computer algebra systems, and this only works for functions that have elementary antiderivatives, or at least let me say that's the most common use for these. You should bear in mind that even the most powerful computer algebra system can't find an explicit formula for some functions that don't have elementary antiderivatives, and so that's an important limitation. The other thing is that these computer algebra systems are only as clever as the people who program them, and often when I'm using these, there are integrals that I end up being able to do that stump the computer algebra systems. Let's begin, however, with our discussion of tables of integrals. Tables of indefinite integrals are very useful. They give you the indefinite antiderivatives. So when we're confronted by an integral that is difficult to evaluate by hand, or we don't have the time to evaluate it by hand, and we don't have access to a computer system, we use these. I have one of these in my office and I use it frequently. There's a relatively brief table that is given in appendices of books, and there are very much more extensive tables, and here's a couple of references. Some of them have hundreds of pages of integrals, indefinite integrals. But it should be remembered, however, that integrals do not often occur in exactly the form listed in a table. Usually we need to use the substitution rule or algebraic manipulation to transform a given integral into one of the forms in the table. This is the version of the CRC standard mathematical tables that I have in my office. I have the 25th edition. That says something about my age, I guess. But it actually has served me very well. My first go-to computer algebra system was Derive, and Derive was actually quite functional, and I liked it a lot, and it served me very well. But this was discontinued in 2007, and the last version I was able to use was Derive 6. So it was the 6th version. I've also used a whole bunch of the computer algebra. These are computer algebra systems. And by the way, Derive, when it was discontinued, it was actually owned by Texas Instrument, and Texas Instrument used it in their calculator products, and in fact this became TI Inspire by Texas Instrument, and this is the successor to Derive. And the last stable version of this was in 2020, at least according to the Wikipedia thing where I got this information. Now there are more of these systems than you can shake a stick at, and I'm just going to comment on some of the ones that I know about and have used. Maple is used by mathematicians and involves a lot of matrix application, and it's used in some engineering schools. MathCAD is used in many engineering schools like Purdue and things like that, and MathCAD is a platform where they do other things that are called MATLAB. So that happens a lot in some of your engineering schools, and when you go there you might find it. Sort of the Cadillac of this, I have a copy of Mathematica, but it's pretty expensive. If you're buying it as a private system, it costs in the thousands of dollars. It was developed by Stephen Wolfram, who was a physicist, and the reason he developed Mathematica was that he didn't have any of the systems that could do the calculations he really wanted to calculate. And this has been a fascinating it's a very sophisticated tool, and in fact Steve Wolfram also has moved on to Wolfram Alpha, where he tries to integrate worldwide databases. So if you wanted to do a calculation based on the GDP of Latin American countries, this product should be able to access that data as well as do the calculation. This is an open source version of Mathematica. And this is what I've been using more lately than anything else, this and Wolfram Alpha perhaps. Now, TI not only has the TI Inspire, but the drive code is actually in this calculator, and this is the calculator I own. It is a TI 84 silver version. And I don't use it a whole lot actually, but I did buy it and it's worthwhile. The first calculator I ever bought when I was a sophomore in college was a TI, although it was not as sophisticated as this. I put a slash to this because I'm not going to let you use this on your high stakes assessment because this has symbolic integration in it. And so you just punch a button and you think you have an answer. Now that doesn't really mean you have an answer because you punched a button. There's a difference between driving a car and knowing how a car works. And I won't go into that too much, but for reasons of level playing field and other things, we're teaching math old school to you, and so you're not going to be using something that has symbolic integration in it. Now, I should do an example, and I am going to do an example, and the example I'm going to do is I'm going to evaluate this this integral, and I'm going to do it using a table of integrals, and I'm also going to use it doing CAS systems. Now, you really should be able to do this. You have the tools to do this, and you complete the square and probably integrate by parts, and it would be a challenging problem, but you should be able to do this. But a year from now, you might not remember how to do all those things, or maybe 5 years from now, as a practicing engineer, you wouldn't know how to do all those things, or maybe have the time to do it, so you might look in an integral table. Now, we're going to use, from the table that I'm referencing, we're going to use formula number 21, but let's talk through the solution a bit. Since the table gives a form involving the square root of a squared plus x squared, it also gives other forms for the square root of a squared minus x squared and the square root of x squared minus a squared, and you recognize all these as trigonometric substitutions, but it doesn't give you the form for this. So the first thing you'd have to do, even if you're using the table, is you'd have to complete the square. So you'd have to complete the square this way, and you should verify that you do that. So you see, even though you have a computer algebra system, that doesn't mean that you don't have to do some math and work. So then we have to make a substitution again here, and that is going to be u equal x plus 1, so x is equal to u minus 1. We're substituting there, and we've completed the square there. So now we've changed this into something that's matching up better with the formula in 21, which was the pattern that we were matching. So this is the indefinite integral of x, and this is the square root of x squared plus 2x plus 4 dx. And after we do this u substitution, we get this. And then we write it as this. So you see, now we have something that matches up with these. So the first integral is evaluated using the substitution t equal u squared plus 3. And so we're going to be able to do that pretty quickly without integral tables. So we do that substitution. And we get this. You should follow this and see that you get 1/2 the square root of t dt. And in the end, it's going to be 1/3 u squared plus 3 whole to the 3/2. Now the second integral here is going to use this formula. And there's formula 21, and we're going to have a, though, because a is a constant, a is going to be the square root of 3. So when I substitute that in here, I get this expression. And again, you should verify that I'm using this pattern to get this expression. Thus, I get, and now I have to go back, because this is an indefinite integral, I have to go back to my original native variable. And so when I do that, I get this first is u from the integral table, and then I'm going to revert back to x. So doing the first integral and the second integral from the integral tables and adding a constant of integration, I am finished with the problem. It is instructive for you to follow all these steps, so make sure you do understand them. Now, I'm going to do the same problem using a computer algebra system. Now, first of all, you have to be really careful to type it incorrectly, and the syntax on these systems is cumbersome. And so it takes some practice. In fact, that's one of the things I struggle with myself, is getting the syntax right. And strictly speaking, you have the tools to do this by hand, and I encourage you to give it a go. Now, I did this with several different systems. Maple responds with this answer if you enter it correctly. And if you get this, some of you might say, well, what the heck is an arc hyperbolic sine? And you're going to find that out later in this course, even though you don't know now. But this is what Maple will give you. Now, this would look different than what you'd find if you actually did the, in fact, when you look at the example that we did, which is the same one, the previous example, this is an equivalent answer, but you say, oh, but I don't have that button on my calculator. No, you don't. You don't have an arc hyperbolic sine button on your calculator. But there is an identity, and we will cover this identity in Calc 2 later, that the arc hyperbolic sine of x is the natural logarithm of x plus the square root of x squared plus 1. In fact, I ask you a question about, this later in the course. So anyway, using this identity, this expression up here becomes, when you're substituting this in for x, or for when you're substituting this argument in and using this identity, you'll get this, and then you use some simplification and more algebra, and you get this. Now, I should note that also when you're doing a calculation and looking to plug something in, this is something you can plug in using your calculator, although it would be difficult to do, and that would allow you to do a definite integral, which is more the kind of problem I would ask. Now, this ln 1 over the square root of 3, and some students will say, Jim, that's the ugliest damn number I've ever seen in my life, but it is a number. And there are no ugly numbers, just like there are no ugly babies. So this is a number, so this actually could be absorbed into the constant of integration if you were just finding a definite integral. Now, if you were to do this with Mathematica, Mathematica gives you a different answer, but it's not really different because they combined the first two terms and the Maple result together to get a single term after they factor. Technology is a blessing and a curse. And you're not going to be using much technology in this course anyway, but as a practicing engineer, I hope you do. I hope you become practicing engineers, and you will have cause to use math. In closing, for now, more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.